Modern humans now cover the planet as a family of billions. And yet, genetically speaking, we are strangely uniform, far more like to one another than other great apes are to their own kind. Back in 1972, scientists first dared to ask why, suspecting that some disaster in our deep past had once pushed our ancestors to the very edge of extinction. For decades, the leading explanation seemed to be a familiar one, the massive Toba supervolcano eruption. But newer evidence has completely torn that theory apart. In its place, a stranger, much deeper crisis has emerged. Could nearly every single human ancestor have vanished around 900,000 years ago, leaving behind only about 1,180 survivors to somehow rebuild our entire species? To understand where everyone else went, we have to start with a strange riddle written directly into our own DNA. A puzzle, hidden in our genes. In the early 1970s, a quiet revolution began inside the world of genetics. Scientists studying human DNA stumbled onto something that simply didn't add up. When they compared our genes against those of chimpanzees and gorillas, they found something genuinely surprising. Modern humans carried far less genetic variation than either of our closest living relatives. For a species that had already spread across every continent and adapted to nearly every climate on Earth, this seemed almost impossible to explain. The question haunted researchers for years: what could possibly have squeezed the entire human species through such a narrow genetic bottleneck? Things took a dramatic turn in 1972 when a landmark study measured genetic differences between people sampled from all around the globe. The resulting data painted a stark picture. At some point in our distant past, human populations must have shrunk down to just a small fraction of their former size. The study's authors called this a genetic bottleneck. For the very first time, the idea took hold that every single person alive today might trace their ancestry back to a surprisingly small group of survivors. But what could have caused such a dramatic collapse? The evidence available at the time was thin, and the tools were primitive by today's standards. Early estimates placed this mysterious event somewhere between 35,000 and 65,000 years ago, though these numbers were really little more than educated guesswork. The true date, and the actual cause behind it, remained buried somewhere in the fog of deep prehistory. The only thing scientists felt confident about was the sheer scale of the disaster. Chimpanzees, for comparison, display nearly twice as much genetic diversity as humans do. It seemed as though humanity carried the genetic scars of a catastrophe so severe that it had shaped the very foundation of our species. For decades, the mystery went completely unsolved. Leading scientists debated endlessly over whether a single catastrophic event could explain such a dramatic drop in diversity, or whether it might have been a series of smaller crises instead. With no fossils, no written records, and only the faintest traces buried inside our DNA, the entire field hit a dead end, simply waiting for a breakthrough that could finally reveal what had really happened to our ancestors so long ago. The Toba volcano. Theory of few scientific theories have ever captured public imagination quite like the Toba catastrophe hypothesis. In the 1990s, the story seemed to fit together perfectly. A massive volcanic supereruption at Lake Toba in Sumatra, Indonesia, unleashed a blast roughly 10,000 times more powerful than the 1980 eruption of Mount St. Helens. Dated to around 74,000 years ago, this eruption scattered ash across multiple continents and, according to early climate models, may have triggered a volcanic winter lasting for years afterward. The idea was simple, dramatic, and easy to picture. An event so devastating it reduced the entire human population down to just a few thousand survivors, neatly explaining our genetic uniformity in one clean stroke. For decades, this explanation dominated textbooks and popular science documentaries alike. Researchers pointed to thick layers of volcanic ash, sudden climate shifts, and the sheer scale of the eruption itself as supporting evidence. But as more evidence accumulated over time, cracks started forming in the theory's foundation. Archaeologists working in India and Sumatra uncovered stone tools and clear signs of continuous human activity running straight through the Toba ash layers. Sites well within reach of the eruption's fallout showed no signs of sudden abandonment or population collapse whatsoever. Human presence simply persisted, tool by tool, layer by layer. A pattern that strongly suggested continuity, not collapse. One archaeologist sifting through these ancient sites noticed something particularly striking. The exact same style of stone tools appeared both before and after the ash had settled. If the eruption had genuinely wiped out nearly all humans in the region, there should have been an obvious break in the record. Instead, the continuity was unmistakable. Climate scientists soon joined the debate as well. Advanced climate models, far more sophisticated than anything available back in the 1990s, suggested Toba's global cooling effect was likely much less severe than originally believed. While the eruption certainly disrupted local ecosystems near the volcano, there was little solid evidence pointing to any kind of worldwide catastrophe. The once imagined planet-killing volcanic winter faded down into more of a regional event with limited long-term consequences. Geneticists began questioning the timeline too. The genetic bottleneck signal preserved in human DNA simply didn't line up with the actual date of the Toba eruption. The numbers just didn't add up. By the 2010s, the scientific consensus had clearly shifted. The Toba hypothesis, once the leading explanation for humanity's genetic bottleneck, could no longer hold up under the weight of all this new evidence. The search for real answers was effectively back at square one, and the mystery surrounding our origins had only grown deeper. A new approach. Using modern DNA. A researcher named Wang Jiehu and a team at the Chinese Academy of Sciences decided to approach this long-standing genetic mystery from a completely different angle. Rather than digging through ancient bones or volcanic ash deposits, they turned instead to the DNA of people living today. Drawing on a global sample of 3,154 modern human genomes, the researchers set out to reconstruct the population history of our entire species by using the present as a window into the deep past. Their main tool was a computational method called FitCoal, short for Fast Infinitesimal Time Coalescent Process. This approach analyzes tiny differences scattered across thousands of individual genomes, hunting for patterns that only make sense if a population once crashed dramatically or later rebounded. By comparing how often specific genetic variants appear across different people, FitCoal can effectively map the rise and fall of ancient population sizes stretching back hundreds of thousands of years. Unlike earlier methods, which tend to struggle seeing clearly through the haze of deep time, FitCoal slices genetic data into extremely fine time intervals. This lets it detect sudden shifts in population size that older techniques would likely have smoothed over or missed entirely. The model works by assuming every new genetic variant traces back to some shared common ancestor, then calculating how quickly those genetic lineages must have merged together as the ancestral population either shrank or grew over time. The dataset behind this research was enormous and genuinely diverse, drawing from people across Africa, Asia, Europe, and the Americas. By deliberately focusing on the neutral parts of the genome, sections not particularly shaped by natural selection, the researchers aimed to capture the true underlying signal of population change, rather than picking up noise from adaptation or migration patterns instead. The analysis required carefully accounting for mutation rates, generation lengths, and even the possibility of hidden population structure hiding within the data. But the real power of this method came from its ability to test all of these assumptions simultaneously across thousands of genomes at once. When the team ran the FitCoal model on this unprecedented dataset, Hugh's group detected a dramatic collapse in the effective population size of our ancestors, not tens of thousands of years ago, but hundreds of thousands of years in the past. The signal was sharp, unmistakable, and consistently appeared across multiple different human populations. Remarkably, this breakthrough didn't depend on a single fossil or archaeological dig site at all. It depended entirely on the collective genetic memory written directly into the DNA of people alive right now. Just 1,280 survivors. The numbers behind this ancient catastrophe are honestly difficult to fully comprehend. At the very lowest point, the breeding population of our ancestors is estimated to have shrunk to just around 1,280 individuals. Not a tribe, not even a small village. Barely enough people to fill a modern high school auditorium. This wasn't a brief dip or some minor regional setback either. According to this genetic analysis, roughly 7% of all human ancestors alive at that time simply vanished from the story of our species. The survivors represented less than 2% of the original population. If a collapse on that same scale happened today, nearly all 8 billion people currently alive would disappear, leaving behind only a small handful to somehow carry our entire species forward. And this wasn't a short-lived crisis either. The bottleneck is estimated to have lasted roughly 117,000 years, genuinely longer than the entire span of recorded human history put together. For more than 100,000 years, humanity teetered right on the edge of complete oblivion, with every single birth and death carrying enormous weight for our future. The genetic consequences were just as severe. Researchers estimate that roughly 85% of our species' original genetic diversity was permanently lost during this extended crisis. Traits, entire lineages, and countless potential paths for future evolution simply vanished with each passing generation. A population that small would have faced constant, relentless threats. Disease, starvation, a single unusually harsh season potentially wiping out an entire family line. The survivors likely lived scattered across small, isolated groups, with every single birth representing a fragile hope pushed up against overwhelming odds. This genetic evidence doesn't simply suggest a modest population reduction. It points toward a bottleneck so extreme that it left a permanent, lasting mark on our DNA, one that every person alive today still quietly carries inside them. This represents the true scale of loss modern science has now uncovered. A near total erasure of humanity, stretching across continents and centuries, held together by nothing more than a single fragile thread of survivors. What the bones reveal. DNA alone can only tell part of the story. Bones reveal something different entirely. Paleoanthropologist Giorgio Manzi has spent decades carefully studying the fossil record, hunting for traces of our most ancient ancestors, and he noticed something genuinely odd. Between roughly 950,000 and 650,000 years ago, the fossil record essentially holds its breath. Sites that once yielded a steady trickle of hominin bones fall almost completely silent. Only a small handful of fragmentary remains have ever turned up from this specific window of time, and even those remaining pieces are fiercely debated among researchers. Some, like the Spanish fossils, classified as Homo antecessor, don't quite match the anatomy you'd expect from direct survivors. Their skulls appear too delicate, their features too distinct from what came both before and after. Then in the reddish sands of Thomas Quarry near Casablanca, Morocco, a partial skull surfaced, dated to roughly 773,000 years old, sitting right at the very edge of that mysterious fossil gap. The skull's notably thick vault and pronounced brow ridge hint at a lineage distinct from those that came before it. It shares clear traits with what later scientists would come to call Homo heidelbergensis, a species now widely recognized as the last common ancestor shared by Neanderthals, Denisovans, and modern Homo sapiens alike. The timing here is almost certainly not a coincidence. This particular fossil appears right around the same time the genetic evidence suggests our population began recovering, offering researchers a rare, direct glimpse of the very survivors who managed to pull through this ancient crisis. Population bottlenecks are already well known to accelerate evolution in other mammal species. When genetic diversity drops sharply, random chance events can lock new traits into a population much faster than usual, sometimes triggering rapid evolutionary divergence. For our ancestors, this crisis may have been exactly the moment when isolation and constant hardship forced a genuine evolutionary leap forward. The distinctive features visible in the Thomas Quarry skull seem to echo forward through the bones of later hominin fossils, found across both Africa and Eurasia. The once mysterious fossil gap now looks a lot like the shadow cast by a genuine near-extinction event. And from that narrow evolutionary bottleneck, an entirely new lineage took root, one that would eventually branch out into every single human being alive on Earth today. The physical evidence remains thin, but the alignment between the genetic data and the fossil record is genuinely striking. For researchers like Manzi, the fossil record isn't just a simple list of missing names and dates. It's a powerful reminder of exactly how close our species once came to disappearing entirely, and how a single skull, weathered by nearly 800,000 years of time, can quietly carry the full weight of our shared survival story. A planet turning hostile around 900,000 years ago, the planet's entire climate system began turning unpredictable and increasingly harsh. Glacial cycles that had once lasted roughly 41,000 years began stretching out to closer to 100,000 years instead, building thicker ice sheets and pulling ever more water and carbon dioxide out of the atmosphere. Atmospheric carbon dioxide levels dropped to some of their lowest points in millions of years, stripping moisture from the land and pushing entire ecosystems right to the edge of collapse. During a period known as Marine Isotope Stage 22, conditions reached a genuine breaking point across large stretches of Africa and Eurasia. Lush grasslands gradually gave way to barren soil and dust. Evidence drawn from isotopic analysis of large herbivore teeth tells this story clearly. Animals that had once grazed freely on abundant grasses were suddenly forced to adapt to sparse, woody vegetation instead, or simply die out. The chemical signatures preserved inside their tooth enamel record a sudden, dramatic collapse in available vegetation. For the early humans who depended on these same animals as a food source, that vegetation collapse was nothing short of catastrophic. One paleoclimate researcher reviewing these isotopic records has described a world where basic survival was no longer something you could simply count on. It had become a daily struggle against a planet growing steadily colder, drier, and far less forgiving. For thousands of generations, early humans lacked even the most basic defenses against a rapidly changing world. Without mastery of fire, there was no reliable source of warmth through freezing nights, no way to cook food and unlock extra available calories, and no easy method for keeping dangerous predators at bay. The archaeological record from this specific period is almost completely silent when it comes to tools or shelters sophisticated enough to soften the blow of such a brutal climate. Survival largely depended on little more than sheer luck and whatever meager resources the land happened to offer. The discovery of fire changes everything. But around 790,000 years ago, something genuinely changed. At a site called Gesher Benot Yaakov, located in what is now Israel, researchers uncovered clear evidence of ancient hearths, solid proof that early hominins had learned to actually control fire. Charred seeds, burned flint fragments, and distinct layers of ash all point toward repeated, deliberate use, not merely accidental wildfires. This breakthrough amounted to far more than just a simple convenience. It represented a genuine turning point for the species. With reliable fire, these early humans could finally cook tougher foods, meaningfully expand their available diet, and stay warm through even the harshest winters. Mastering fire tipped the balance decisively, transforming sheer vulnerability into real resilience and setting the stage for a dramatic population rebound in the generations that followed. Not everyone is convinced. Of course, skepticism soon followed the headlines. In 2025, a team led by John Terhorst published a pointed critique questioning whether the dramatic population crash originally detected by Fitcol was actually real, or possibly just a statistical mirage. Their analysis used the very same underlying genetic data, but applied several alternative computational methods instead, including tools known as PSMC, MSMC2, and RELATE. None of these alternative tools found evidence for a bottleneck nearly as sharp or as ancient as the one Fitcol had originally suggested. Terhorst argued that the Fitcol algorithm might be mistaking complex population structure, or perhaps ancient migration patterns, for what looks like a sudden dramatic collapse, especially when analyzing genomes drawn from groups with long, complicated histories of separation and later remixing. Other researchers, including Dravasla and colleagues, proposed an entirely different explanation, that modern humans might actually descend from two or more distinct ancestral groups that later merged back together, rather than surviving through one single tiny bottleneck population. And yet, even as this particular debate sharpened, new supporting evidence kept surfacing elsewhere. A 2024 study led by Damiano Marchi pointed to widespread mass migrations and large-scale megafaunal extinctions occurring right around 900,000 years ago. Clear signals that something genuinely extraordinary was reshaping the world during that same period. The exact question remains unsettled today, but the combined weight of climate evidence, extinction patterns, and genetic clues continues to keep this mystery very much alive. What this means for us today. Every single human being alive today may quietly carry the genetic legacy of just 1,280 ancient survivors. As climate change once again tests humanity's resilience in our own time, the lesson embedded in this ancient story feels genuinely clear. Survival has always depended on adaptation, never on some guaranteed inevitability. Our shared origins serve as a powerful reminder. Existence itself is fragile, and progress is never something we're simply owed. The next chapter of our species' story depends entirely on what we choose to do right now. What will our own descendants eventually say about us?